12.2 is about the derivative of products and quotients. And the key thing that you're going to need to be able to do in the products and quotients is to make sure that you understand that you're going to have to take two separate sets of derivatives before you combine them into the final derivative. And that'll make sense as I do the examples. I actually pulled out the slides that have the rules on them because the rules, if you look at them, there's not a good way to say it that makes it make sense. It's easier to understand it if you see me do it than it is to just look at the rule and try to figure out what it's saying. So to get started, we're going to start with product rule. This is, I hope obviously, a product. This is factor number 1 and factor number 2. The first key is to realize that you have two pieces of a product, and those two factors each have their own derivatives. And we're going to do those derivatives separately. And I'm going to try to color code because I think it's easier to follow when you do it that way. Before I tell you how to do the final part of the rule, what I want to do first is make sure that we can do the two separate pieces we're going to need. So the derivative of 2x plus 3 is what? It's just 2. Okay? And the derivative of 3x squared is 6x. Now this is what the derivative rule says to do. To find f prime, with a derivative finding when you're finding the derivative of the product of two factors, one of the things that you're going to do is you're going to be adding up some pieces. So it's going to be a sum. The sum is going to be the first product, part of the product, the first factor. In this case, the first factor is 2x plus 3. And your second factor is 3x squared. And then they're going to swap each other's derivatives. The derivative to the second one is going to be multiplied times the first one. Okay? And then the derivative of the first one is going to be multiplied times the other factor. So basically what you're going to do is you're going to separate out your two factors, take the derivative of each factor, make sure you write those down. Then you're going to swap the two, and you're going to give the second factor's derivative to the first factor, and your first factor's derivative to the second factor, and add it all together. So 6x times 2x is 6 times 2 is 12x squared. 6x times 3 is plus 18x. And because it's addition, we don't have to worry about sign changes at this point. And then 3x squared times 2 is 6x squared. And then you probably, just for the sake of less typing, since it's not hard to do, you'll probably want to combine those two like terms. 12x squared plus 6x squared is 18x squared plus 18x. So there's your derivative. Okay? Now, it is not necessary that you actually do this, but I'm going to try to make a point to you. I can check this and make sure that I did it correctly. I can check it on the calculator, for that matter. But I can also check it by multiplying out f of x. If I take f of x and take 3x squared times 2x, I get 6x to the third power. And if I take 3 times 3x squared, I get 9x to the second power. And if I take the derivative, f prime of x, I get 3 times 6 is 18, x to the 3 minus 1 is 2 power, plus 2 times 9 is 18, times x, because 2 minus 1 is 1. For this problem, it's really a wash which way you do it. Both ways are perfectly satisfactory. It's easy to do it both ways. But if these had been a little bit more complicated factors, it might not have been nearly so simple to do this. And that's why we actually have a product rule that lets you find the derivative of more complicated products than this. You ready to try another one? Now this one's a little more complicated. That's why I said, you can multiply it out, but multiplying this out could get ugly. So when we start working with this one again, you want to pay attention to the fact that you have 2 sets of parentheses. Therefore, you have 2 factors. So I take the derivative of each one of the factors. And I know here that I'm first going to have to convert x that's the square root into x to the 1/2 plus 3. And then that derivative is going to be 1/2 x to the minus 1/2 plus 0, which is going to be 1/2 x to the negative 1/2, or anything else you want to try to simplify it to. But I try to do as little simplification as I can, because the more simplifying you try to do, the more likely you are to make a mistake, and then later on that mistake gets compounded. So as far as I'm concerned, I'm done. This is the derivative of the first factor. My second factor is x squared minus 5x, and its derivative is far easier. Its derivative is 2x minus 5. So now I'm ready to take the derivative y prime. So I'll start out with my first factor. I just copy it down. You can change it to the power version, or you can leave it with the radical. It doesn't matter. And then I'm going to give it the derivative of its partner. And then I'm going to add, and I'm going to put down its partner, the second factor. And give it the derivative of the first one. And this is the part where you get surprised. You're done. Yeah, you can clean that up. But that's just algebra. I don't care if you clean it up or not. If you know how to type that into my math lab the way that you should, and by this, you've had enough experience by now, you ought to be able to put almost anything in my math lab. So if you can type that into my math lab properly, that is the right answer. And if you're doing something for me, I know that's the right answer. What I want to see is I want to see your steps in between and your final answer. Ordinarily, when I give a quiz on these, I always have somebody that tries to simplify this or tries to simplify it further. I get down to the step where I know the calculus took place. If the calculus was right, I never even look past that. I'm done. Because there's so many opportunities to mess it up that weren't calculus. So if you can get this far, you're done. Okay? This is not algebra class anymore. We'll do algebra when we need to be able to do the calculus. I'm sure my algebra teacher would be spinning in her grave right now. That's okay. I was a math major, you're not. Okay? Let's try another one. This is a quotient rule. It works similarly. It is not identical, but it is very similar. In a quotient rule, you have a numerator and you have a denominator. The way that it works that's different in a quotient rule, you're still going to take the derivative of the numerator, which is 2. You're still going to take the derivative of the denominator, which is 4. And then the way the quotient rule works, you have to be a little more careful than with the product rule, because order makes a difference. You could have done second times derivative of the first plus first times derivative of the second. You could have swapped the two pieces in a quotient rule back and forth because that's addition, and it doesn't matter. But this is not going to be addition. This is going to be subtraction, and order makes a difference. So f prime, you're going to lead off with the denominator. Always go to the bottom first. The denominator is 4x plus 3. Just like with the quotient rule, with the product rule, it swaps derivatives with the numerator. So it takes the numerator's derivative, which is 2. But rather than add, it subtracts. Then it takes the numerator, and the numerator partners up with the denominator's derivative, which is very much similar to what we did before, except we're subtracting, and we had to start with the denominator, and then you also end with the denominator. And the denominator actually gets squared. It's the denominator times itself in the derivative denominator. Okay? A little more complicated. And here again, if you get that far, if I see that you've got this far and you mess up the next step, I'm not really going to be terribly upset. But there are going to be cases where you don't want it spread out quite this way, because it'll be difficult to type in. So for that reason, we might want to try to collect up some like terms, because when it's convenient, we will. So 2 times 4 is 8x. 2 times 3 is 6. Negative means we're going to subtract all the rest of these. 4 times 2x is 8x. 4 times negative 1 is negative 4. We are not doing anything with that denominator. It can stay just like it is. There's no need to factor it out or multiply it out or try to cancel it. Just leave it alone. So then f prime of x, in a little more compact form, so you're less likely to make mistakes when you type it in, we have 8x minus 8x, which disappears. 6 minus negative 4 is 6 plus 4, which is 10, over 4x plus 3 in parentheses squared. You're done. This was the most important step. Be sure you get that step correct. The only reason to do this step is because it makes it easier to plug in a number for x, because you only have to plug it in one place. Okay? So what the rules have in common is you take the derivative of the pieces and then you swap their derivatives among them. If it's a product, you add and you're finished. If it's a quotient, you start at the bottom, swap the derivatives, subtract, end at the bottom by squaring the denominator. And I'm going to want you to do a lot of practice on these so that you'll get good at these. This one uses both rules together. Please don't try to do both rules together. Do them one at a time. So all over the denominator squared. So on this one, I know eventually that's going to be 7x minus 9 in the bottom squared. But when I look at my numerator here, the first thing I notice in my numerator is that my numerator is a product. So before I can take its derivative, I have to either multiply it out, which you can do, that's fine. You can multiply it out and take its derivative, or you need to use the product rule on it. Now, I don't care which one you do. Either one works. But since this is a product, I'm going to do the product rule on the top. So since my numerator is a product, my numerator is going to be the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. And then since I'm going to have to take that derivative again, I'm going to have to take the derivative of this whole mess. I'm going to have to use that derivative in some way. I'm going to try to shrink it down. So 5 times 3 is 15 minus 12x plus negative 4 times 5 is negative 20. 20x, thank you. I said 12x too, didn't I? And then 4 times 5 is negative 20x. 1 times negative 4 is minus 4. So minus 20x plus minus 20x is minus 40x. And 15 minus 4 is plus 11. So this is n prime. And I would a whole lot rather use that derivative in the next calculation than I would of that big long thing, even though it would have been right. And then, of course, the derivative of my denominator is not hard at all. So d prime is just 7. Okay? But I had to use the product rule in my numerator. So that's why it was so much more work. So now I'm ready to take the derivative with respect to x of the quotient. So the derivative of my numerator times my denominator. My denominator is 7x minus 9. Always start at the bottom. The derivative of my numerator is negative 40x plus 11. My rule says I'm going to subtract my original numerator. Don't go back to this. My original numerator. 3 minus 4x times 5x plus 1 times the derivative of the denominator, which was 7. And I'm going to put it all over the denominator squared, which is 7x minus 9 squared. If you want to quit there, you're fine. Okay? If you want to quit there, you're fine. Yeah, I know it's ugly. All of my colleagues, especially Mr. Thacker, would be horrified. But they're not going to have to write big, long sentences to answer their questions either. And you are. Now, if you want to simplify it, go ahead. I'm not going to. Simplified answers in the book. If you can do this one, you can do just about anything. Okay? So in the few minutes we have left, we're going to talk about a new concept where we're going to use what we just learned. We're going to talk about average cost. How many people in here have already had a statistics class? What's the most common average? What we usually think of when we talk about average? The mean. You take the total and divide by how many, right? That's the same concept of average we're going to have here. If you have y is equal to c of x, that gives you the total cost to manufacture x items. So if I want to find the average cost per item, that word average tells me exactly what I'm going to do. I'm going to take the total cost and divide by how many, which is going to be the number of items. And that's going to give me what I will call the average cost. And I use it as a function notation because usually the cost is not given as a number, it's given as some kind of an algebraic expression. So that means the average cost is also going to be some kind of an algebraic expression. Now there is going to be one time where actually writing it this way is going to be a pain. So I want you to keep in mind that sometimes it's easier to write the average cost this way. It's that same little trick that I showed you when we were doing the four-step method of rational expressions. Sometimes it was easier to let h approach 0 if you could get it out of the denominator, and yet you were stuck with it because you were dividing by it. But if you multiplied by 1 over h, then you could cancel out your h's. That's going to sometimes be the case here to make you have a simpler average cost expression. So as we do examples, I'll show you when it's better to do that. Sometimes it's just as easy to do this, but sometimes it's simpler to do this. And just realize that everything we said here applies to revenue and it applies to profit. So you can have average cost, average revenue, average profit, and you can take the derivative of your average cost, revenue, or profit and have the rate of change or the marginal average cost. Marginal still means take the derivative, okay? So that's what we're really going to be looking at. And we're going to look at an example of that before we leave. Because one of the things, as you might imagine, is if you're in a business and you're manufacturing something, the thing that you want to maximize is your profit. Sometimes you don't have as much control over revenue as you would like to. It's kind of hard to manage your revenue and figure out how to maximize your revenue, because sometimes you make too few and you can still make more money, and sometimes you make too many and then you got them sitting on the shelf and wasting your money. But you can minimize your cost. You can look at ways to minimize your cost. And that's why this is important to find your average cost. Because what you're going to see is that in the beginning, your average cost, which is your cost per item, is going to be pretty high. But as you make more and more and more, your average cost generally shrinks. But it doesn't continue to shrink forever. At some point, your average cost per item is going to stop going up and start going back down. In other words, its rate of change is going to become negative. It can also start out really, really high, bottom out, and then it can start increasing again. When that happens, you really want to know what that minimum average cost is, because that's probably where you're going to find your maximum profit, since you can't really control revenues effectively. So we're going to talk a lot about that in Chapter 13, but we can do a problem like this now. So here we've got a cost function. This cost function is only good when x is between 1,000 and 200, or 20,000, essentially. So between 1,000 and 20,000 is really what that says. Find the average cost per 100 motors. Well, first of all, the average cost is this cost divided by x. And that's actually the expression for it right there. But that means if you were to have to take this derivative, you would have to apply the quotient rule here and then do it a second time to be able to do this as the other quotient. I just as soon not have to do two quotient rules for one problem. How about you? Okay, this is where the trick helps. So rather than dividing by x, we're going to multiply by 1 over x, just because it gives us a cleaner expression. You multiply straight across. So the numerator remains 3x squared plus 120. But the denominator becomes 2x squared plus x. Now, I could have left it factored. Then I had to do a product rule. I didn't want to do a product rule either. So I wanted to do enough simplification that I could do the least amount of work possible to get the derivative. This isn't hard to take the derivative of. So now that I've got it, I have a numerator. And I have a denominator. And if it asks me to find marginal cost in the next problem, which it's going to, I'll be easily able to do that. But it says find the average cost per 100 motors. You need to finish up this expression by saying what this is. So this is 3x squared plus 120x over 2x squared plus x dollars per x 100 motors. So this is your average cost function. And it includes both the algebraic expression and the units that tells you how it's measured. And then the next part of the problem says find the marginal average cost. Translation means what you're actually being asked to do is to find out how fast the average cost per X 100 motors is either increasing or decreasing. You're very much interested in when it's decreasing. And you're even more interested in when it stops decreasing. So to find that average cost, we're going to find C average prime of X, which means we're going to take the denominator, because remember it's product, and we're going to pair it up with the derivative of the numerator, which is just 6x, because it's 3x squared plus 120. And from that, we're going to subtract the numerator, times the derivative of the denominator, which is derivative of 2x squared is 4x, and the derivative of x is 1. And then we're going to divide by the square of the denominator, and the denominator is 2x squared plus x, and that quantity is squared. And at that point, cleaning it up is optional. But the correct units here are, this is the expression, and this again is it's increasing or decreasing in dollars per X 100 motors, even though it's talking about the average. We'll mention that if we actually have a number to go with in there with it. Okay? Now, before I move that, does anybody have any questions about how I got where I did? We all good? Okay. So what we're going to see in the next chapter is that the average cost is generally minimized when the marginal average cost is 0. We want to find the level of production that minimizes the average cost. In other words, we want to set this rate of change to 0. What value of x causes the value of this whole thing to be 0? Let me recopy it first. That's what we want to do. We want to solve that. Now that looks pretty terrible. But I want you to take one thing into account first. Does it really make a hill of beans what this comes to? Because what needs to be 0 for that quotient to be 0? Only the numerator, right? We don't really care what the denominator does, as long as it never equals 0, and it's never going to. Okay? I mean, even if we plug, well, it might if you equal 0, but then again, that means you don't make anything, so that's not something to consider. The only way this is ever going to be 0 is if the numerator equals 0. That's all we really care about, finding a value that's 0. So what we're going to do is we're going to take that 2x squared plus x times 6x minus 3x squared plus 120 times 4x plus 1, and we're going to find out where it is equal to 0, because that's really what we care about. And it would be easier to do that, sadly, if we simplified it. Remember, we only do any kind of simplification, any kind of algebra, if it helps us do something else. This time it's going to help us, because I don't think I want to figure out what causes any of that to be 0. So the first thing I'm going to do is we're going to go ahead and multiply this all out. 2x squared times 6x. 2 times 6 is 12x to the third power. X times 6x is plus 6x squared. 3x squared times 4x is 12x squared, and there's a reason I'm not writing it down here. 120 times 4x is plus 480x. I'm sorry, and that should have been 12x cubed, not squared. And then 3x squared times 1 is plus 3x squared. And 120 times 1 is plus 120. But I'm going to subtract all of those, which means I need to change all those signs before I combine with the rest of this. So that's going to be minus 12x cubed and minus 3x squared and minus 480x and minus 120. And I'm ready to say hallelujah when I realize that the cubes cancel out, because I have no clue how to solve something that has a cube. So 6x squared minus 3x squared is 3x squared minus 480x minus 120 is equal to 0. That's a quadratic equation. I can solve using quadratic formula, but it would be ever so much easier if I first realized that I could divide every term by 3, so that I wouldn't have such large numbers to deal with. So that leaves me with x squared minus, let's see, 160 x minus 3 goes into 120 40 times equals 0. Now, if you want to fool with factoring it, have at. My 1630 students don't like factoring. But quadratic formula works every time. We can do it by quadratic formula. So I'll get another piece of paper here to make sure I have plenty of room to write this. I need to know where this is 0, so A is equal to 1. B is equal to negative 160. C is equal to negative 40. And X is equal to the opposite of B plus or minus the square root of the value of B squared minus 4 times A times C, all divided by 2A. So X is equal to the opposite of negative 160 is positive 160, plus or minus the square root of negative 160 squared minus 4 times 1 times negative 40, all divided by 2 times 1. So now I need a calculator because I can't square 160 in my head. That's 25,600. And 4 times 4 is 16, and the 0 makes 60. So 4 times 1 times 40 is plus 160 because negative times negative is positive. So I have 160 plus or minus the square root of 25,760 over 2. So the square root of 25,760 we'll call that 160.50. And that's all going to be divided by 2. So if I take 160 plus 160.5 and I divide that by 2, I get 160.25. And if instead I subtract, I get negative 0.25. Which answer do I go with? Has to be the positive one, right? It has to be the positive one. Because the negative one doesn't make any sense because X represents the, let's see, production level. Well, you don't have negative production. But you remember at the beginning I said that we didn't really need to worry about if X was equal to 0. Well, if you're rounding negative 0.25 to whole units, how many units is that? None. So that answer makes no sense. It's not useful. But the other answer is 160.25. Well, you can't make 160.25 units either. So we need to look back at the units and see what the actual units were. And that's X hundred. That's X hundred motors. Therefore, the average cost per 100 motors is going to be minimized when you make 16,025 motors, because that was 160.25 hundred motors. Does that make sense? Exactly. And so, as long as you have the same general sense of things. But the key was to understand that that number X doesn't tell you the answer to the problem by itself. So not just because your boss says, when you go in and say, well, X is 16.2 or 160.25, it looks at you like you have two heads, because he's saying, what? What is this? Minimum average is 160.25. What are you talking about? Well, and 160.25 by itself doesn't really give you an answer to the question. But if you go back and look at your units, that's why units are so important. You go back and look at your units, that last sentence, that conclusion, that makes your boss happy. He knows he's not going to be, he needs to make that many and no more to minimize his cost. Otherwise, his cost starts going back up again. Okay? Now, if any of you are wondering, where do they come up with these equations? They pay people like me to gather data and fit models to those equations to come up with those formulas. No, that was a job that I decided I didn't want, because I didn't like living in windowless rooms and talking to computers all day. I like interacting with people, and I've always loved teaching. Okay, so that actually wraps it up for us, and it is 9 o'clock. Quick caution, and I will open by reminding you of this next time. Just as the derivative of a product is not the product of the derivatives, it is the two derivatives swapped and turned into a sum, and the quotient of the derivative of a quotient isn't the quotient of two derivatives. You have to use the process. That's very important. And just as an example, it also, when we did example 3, you can't do that, because you're canceling into a term, not a product. Be very careful of that. That's something you may have forgotten because you've not done that in a long time. So if you're going to try to simplify, just be aware you can't cancel unless you factor first. Okay? So we are done for the night, and I hope to get your tests all graded and finished and grade reports done by Monday. I would have probably already had them done, but I was kind of tied up.
Will that be posted as well, or
Shelby.
Oh, Shelby.
Shelby. There will be a folder where you turned your test in. That's where I'll actually grade your test. That way you still got your test and you can use it to study by. And then there's a separate folder that'll pop up that says Exam 1 grade reports. And it'll tell you every grade you got and where you currently stand right now. Okay?